Good morning, students. So in the last class, I completed the chapter solutions. So in the today's class, I'm going to start a new chapter, that is coordination component. Coordination. Students, it carries total 8 marks. Okay, in that 3 marks, 2 question, 2 marks, 1 question. Okay, 3 marks 2 question, 2 marks 1 question, so totally it carries 8 marks. So in that, I'll explain. So which one carries among 3 marks, 1 is compulsory, like that, whatever the things I said in the DNF class, similarly in this chapter is also there. I'll explain the concepts. Okay. So in this coordination compound, students, we are going to study the objectives of this is we are going to study first one is Warner's scale. Okay. Second one is definitions of terms in coordination compounds. Next, the nomenclature. Their nomenclature. Next, their hybrid structures or hybridization of CONH3 plus COCl6 minus NiCl4 2 minus NiCl4 2 minus. So among these four, one is compulsory for 3 mark. Among these, one is compulsory for 3 marks. Next, isomerism. Okay. Next, octahedral splitting. And tetrahedral splitting. Magnetic momentum property. Last one is uses of the coordination compound. So these are all the objectives we are going to study in the coordination compound, students. So in this, nomenclature is compulsory for 1 mark. 1 mark means, as I told you, 2 marks, 2 questions are there. In the normal isomerism, 1 question can arise for 2 marks, and the postulates of formal theory is for 2 marks. Understood? Postulates, and here in the definitions, the ligands are there, what type of isomerism is there, and what type of coordination number is there. That is, this is for 2 marks, 3 marks, 1 marks, 2 marks. So totally it contains for 8. It consists of 8 marks in the overall examination. Okay. So they may ask different questions, students. In the isomerism, optical is there, geometrical is there, cis-trans is there. Okay. So they are going to ask the way they want. Okay. That is isomerism. In that, different is there, that is linkage is there, coordination is there, hydration is there. No, different types of isomerism are there. So those are all going to explain in this. So first one is Warner's theory, definition of terms, nomenclature, hybridization, isomerism, octahedral splitting, magnetic properties, uses. Okay. So we will discuss one by one. So students, first, so what are our coordination compounds means? So listen, we know organic compounds and inorganic compounds. And the inorganic compounds, they are called again classified as elements, salts, and etc. Okay. So in that student, especially the inorganic salts, they are classified into what? Double salt, simple salt, and a complex salt. So this coordination compounds means. So as I told you, it is an example of inorganic salt. So this inorganic salt may further classified into simple salt, double salt, and complex salt. So I write example for simple salt, that is NaCl. Example for double salt, that is potash alum emerald. So what is potash alum? Aluminium, potassium aluminium sulfate. So An2SO4 thrice into K2SO4 into 24H2. This is called as what? Potash alum. Okay. So instead of that, another one is there, that is more fun. That is FeSO4, Fe2SO4 thrice plus FeSO4 into NH4 twice SO4 into 6H2O. That is more salt. That is more salt. FeSO4 NH4 twice SO4 into 6H2O. Another one is that KCl into MgCl2 into 6H2O called as carbonite. So these are called as double salt students. Here the mixture of here NaCl means only one salt, Na plus and Cl minus minus. Okay. Here double salt means aluminum sulfate is one salt, potassium sulfate is one salt. So they are together. That's why it is called as double salt. And the last one is that is complex salt. Example is CuNH3 4 times 2 plus COCl6 minus. So these are the examples for complex salt, and this type of salts are called as coordination compounds. Coordination compounds, and these are called as ionic compounds. Okay, why these two called as ionic compound? Why these are called as coordination compounds? Means, so students, the bond between these two is okay here. So as I write here means, so remember here. NaCl assume. Here what happens? Na plus and Cl minus. Correct? That means complete transfer of one electron from sodium to chlorine takes place. Here, the electron from sodium transfer to chlorine, they attain the update configuration. So transfer of ions means ionic bond from one atom to other atom. So complete transfer of electron. Only one electron. Remember, only one electron is transferring from here. They are based on their oxidation state. Okay. Next, if you want FeSO4, FeSO4 means Fe plus 2 plus SO4 2 minus. Here also 2 electrons, complete transfer of 2 electrons from iron to sulfate takes place. Correct? But if you consider this student, COCl 6 times. Here, this is 3 minus, means the oxidation state of cobalt is plus 3 plus 6 into Cl minus. Remember, plus 3, 6 into minus. What it means? Here only 3 electron transfer takes place, but this reaction cannot take place like these students. So here this cobalt has empty orbital. Okay, to the empty d orbitals, the lone pair electrons from the Cl, they completely transfer to empty d orbital. Not only here, so the lone pair electron present, both the electrons from only one atom transfer from chlorine to cobalt. As in here, the lone pair electrons are there, that is non-bonded electrons. Those lone pair electrons completely transfer to this one and they are shared between this cobalt and Cl. So if you want to write the bond, students, so for NaCl you will write the bond like this, ionic bond. For FeSO4 also you will write, so this is what ionic bond. CL6, you are going to write like this. So this shows what? The direction, the arrow, backward arrow shows the electron transfer takes place from chlorine to cobalt. This type of bond is called as coordinate bond. That's why this type of complexes are called as coordination compounds. Why? Because they have a coordinate bond. What is a coordinate? The complete transfer of pair of electron or a lone pair of electron transfer takes place from one atom to another atom. So the one atom to the central metal atom and they share it between these two atoms. Okay. Similarly, NH2 means here also lone pair electrons are present. Right? Those lone pair electrons involved in the bonding. That's why this is called as coordination compounds. It is a type of complex salt students. Okay. So this is all about the types of salts. In organic, there is simple salt, double salt, and the complex salt. So if you want to dissociate this, assume instead of here it is Cl2. This is the compound. So if you dissociate students FeSO4 into NH4 twice SO4. I will write here only. If you dissociate this, you will get Fe plus 2 plus NH4 plus SO4 2 minus plus H plus OH minus. So once this salt dissociate, you will get individual ions. So here it is Na plus and Cl minus. Here if you dissociate these students, you will get Cu NH3 4 times 2 plus 2 Cl minus. So this is the dissociation. So in all the cases, whatever may be the simple salt or a double salt, we will get what? Individual ions. They retain their identity in the solution. So, they lose their identity in the solution because ferrous sulfate is there. After we had solvent, if the ferrous sulfate is dissolved in what? Solvent, the Fe plus 2 ions will separate to SO4 2 minus ions will separate. So then it results in what? They loses their identity. Here, the complex ion is dissociated like this. This is the complex, this is the simple ion. This is the complex ion, this is simple ion. So, there may be a chance of less losing identity. There, the identity loss is very less here because we get a complete complex. The complex is complete, rather the salt is completely depends upon this what? Macromolecule. Okay, so this is coordination compound, how they classified. So coordination compound ultimately it is a simple complex inorganic salt. It consists of one complex ion and one simple ion. Okay, so now I'll write the difference between double salt and the coordination and the double salt and the complex salt. double salt and the complex salt. Okay. So here it only exists in solid state. Okay. It exists in solid as well as solution state. They exist solid as well as solution state. Okay. It dissociates respective ions when dissolved. The dissociate respective ions when dissolved in suitable solvent. Okay, they dissociate into what? Respective ions. Here they cannot easily dissociates into simple ions. So they cannot easily dissociate into simple ions, but here they dissociates into simple ions. Next, it loses its identity in the solution. It loses its identity in the solution. So it never loses its complete identity. Remember, I am mentioning here, it never loses its complete identity. It loses its identity, but not complete, because here the presence of the complex ion will takes place. So the formation of the complex ion will takes place. Thus results in what? It shows at least some amount of the identity. Okay. So here the property of the double salts, the property of the double salts is depends on all ions. Okay, here property of the complex salt depends on complex ion. Okay, the last one is the example you write potash argon. Here you may write CONH3 4 times Cl2. So this is the difference between double salt and the complex salt. Here what happens, students, if the double salt they exist in the solid state, but the complex salts they exist solid as well as in solution state. And they dissociate, give a respective ions. Okay, if they dissociate in a certain solution suitable solvent means, so if they are in a solution they form a simple as well as complex ion. Okay, next. It loses its identity in the solution. It never loses its identity in the solution. The property of the double salts depend upon what? All ions. The property of the complex salt is depends on complex ion. And these are the examples. So this is the difference between double salt and the coordination complex salt may be the answer for 2 marks. Differences wherever the asked students that may carries 2 marks. Okay. Next, we will discuss about the oneness. Next, we will discuss about oneness. So this is here. Oneness. So Werner is the first scientist who studied about the Alfred Werner. His name. Alfred Werner, called as father of coordination compound. Alfred Werner was the first scientist who is called named as father of the coordination compound because the first scientist studied about that type of compounds in the year from the year 1866 to 1919. Okay, students, what he did, what is the experiment of this Alfred Werner means he used to take different halides from the D block elements. Okay, he considered the different halides of the D block element and he subjected them to react with the different moles of ammonia. So first what he did, so 1 mole of, he considered Cl3 cobalt trichloride. Here cobalt is in +3 oxidation state. This one is taken as a primary reactant. So 1 mole of COCl3 he made reacts with 6 mole of ammonia. Okay. So then he assumed the structure may be in this form. Okay. Next. So 1 mole of COCl3 with 5 moles of ammonia. So this is COCl3 into 5NH3. Next, 1 mole of COCl3 plus 4 moles of ammonia that gives COCl3 into 4NH3. Similarly, again you did it for the same thing. COCl3 plus 4NH3, that is COCl3 into 4NH3. This is 1 mole, this is 4 mole. 6 moles of NH3, 5 moles of I will simply take like this. So 1 mole of COCl3 reacts with 6 moles of ammonia, we will get that answer. Okay, students? So then here we will get yellow color. When we get this compound, we will get purple color. Okay. Here it is again green. Here it is violet. So students, when we conducted the experiment, when we start reacting this COCl3 molecule with the different moles of ammonia, we get different color solutions. So first, for this we got yellow color solution, for here purple, green and violet color solution. So here, in this and here in both the case, the molecular formula is same. Then only here it is green color, here it is violet color. So based on these experimental suspects and experimental results, he tried to explain that again. So what he did, he made reacting these resulting molecules with the AgNO3 solution. Okay. So he start and love this color, students. So this is first step. He got different colors. Here it is, and right here. Yellow, yellow color, purple color, green, white. So then, to conclude, what is the reason further experiments being made reacting this with AgNO3 solution. So the resulting solution, whatever the resulting solution is here, that is subjected to what? AgNO3. AgNO3 added to this solution, then we will get 3 moles of AgCl. So here it reacts with AgNO3 means here we got 2 moles of AgCl. So when we make AgNO3 solution to react with these two, both I write. So we have 1 mole of AgCl. So students, here we have 3 moles of AgCl, here we have 4 moles of AgCl, here we have 1 mole of AgCl. When AgCl will form? When the Cl atom present here can react with this AgNO3. Okay, so this NO3 displaces the Cl and will form AgCl solution. Here we have how many moles? 3 moles. Here 3 chloride atoms are there. Here also 3 chloride atoms are there, but the resulting solution is 2 mole of AgCl. That means what? Only 2 Cl atom reacts with AgNO3 to form 2 moles of AgCl. Here also 3 Cl3 is there, but we have 1 mole of AgCl. That gives what? Only 1 mole of or 1 Cl atom reacts with AgNO3 to form AgCl. So based on this experiment, students, we assume the structure of the compounds like the first one is CO NH3 6 times Cl3. Next, second is CO NH3 5 times Cl2. And third one CONH3 4 times Cl2 Cl. So in the first 3 Cl atoms are outside the coordination sphere. They are free, so they easily react with AgNO3 to form AgCl. That's why we have 3 moles of AgCl. Here it is Cl2, that is 2 moles of AgCl. Here it is Cl, that is 1 mole of AgCl. So based on these experiments, students, so first we reacted the CO-CO3 molecule with the different moles of ammonia, you got different color solution. So that is those different color solutions is treated with the excess of AgNO3 solution, then they form different moles of AgCl. So based on the respective moles of AgCl, we assume the compounds may be in this form. So these compounds are called as co-ordination compounds. This type of compounds are called as what? Co-ordination compounds. Here, we assume we introduce, okay, here, as I told you, this is +3, this is -3 means the valency is 3. But here, how many bonds are bonded? 6. Valency is 3, as I told you, +3 state. For example, NaCl you take means valency of NaCl is 1, you will write, right? If MgCl2 you take, valence is 2 you will consider, correct? But here, for AlCl3 is there means valence is 3. Similarly, COCl3 is there means valence must be 3. But here how many bonds are bonded here? 6 bonds means the valency and the number of bonds is here different. So, we introduce a word secondary valency. So, we introduce a word secondary valency. So, students, the central metal atom have the primary as well as secondary valency. The secondary valency is called as co-ordination number. Okay, so based on this, explain some of the postulates, and remember these two, even though they are the same molecular formula, but they give different colors because the arrangement of the atoms are different. Okay. Okay, I'll explain you later the postulates of the theory. You remember this thing, I read the postulates of Oneness. Okay. Postulates are important for 2 months. Postulates of coordination and postulates of Werner's theory. So, first one, the metal atom in coordination compound shows two types of valencies. The coordination, the first one, the metal atom in coordination compound shows two types of valency. So one, primary valency, another one is secondary valency. So in that, primary valencies are ionizable and are and they are satisfied by negative ions. Okay, primary valencies are ionizable and they are satisfied by negative ions. Next, secondary valencies are non-ionizable and satisfied by neutral molecules or are negative ions. Okay. So the metals, the ions are the molecules, not metals. The ions are molecules bounded by secondary linkage, that is secondary valency, have characteristic spatial arrangement. Characteristic spatial arrangement correspond to results in coordination polyhedron. Polyhedron means different structures. So these are all the postulates of Werner's theory. Metal atom in coordination compound shows two types of valency. Primary valency are ionizable and they are satisfied by negative ions. The secondary valencies are non-ionizable and are satisfied by neutral molecules or negative ions. Next, The ions or the molecules bound by a secondary linkage have characteristic spatial arrangement results in the coordination polyhedra. So students, as I told you, I will take the example of to explain this. I take CONH3 5 times Cl2. Okay. So here this one is called as what? Again I have a comparison CONH3 6 Cl2. Remember this and this. So students, the metal atom in coordination compound two types of valency. So this is one valency that is primary. This is another valency that is secondary. Here also this is primary, this is secondary. You may say this is primary, this is secondary. So the atoms which are bonded to the central metal atom inside the coordination sphere is called as secondary valency. Outside the coordination sphere, that is primary valency. Again they said what? The primary valencies are ionizable and they are satisfied by negative ions. So not only negative ions students, they are also satisfied by positive ions. But here the Varna was the scientist discovered proposed this coordination compound means. So here he considered ammonia. Ammonia is a neutral molecule, so it is plus in charge. So of course the primary valency is satisfied by the negative ions like Cl atoms here. Okay. Next, secondary valencies are non-ionizable and are satisfied by neutral molecule or negative ions. Here, consider this example. Here, the charge is 0. Here, the charge is -1. So, this secondary valency here 6. Here, 5 plus 1 means 6. Okay. The secondary valency is satisfied by neutral molecule that is NH3 and also negative ions. Okay. Secondary valency is satisfied by either neutral molecules or negative ions or both. Here neutral molecule is also there and negative ion is also there. In both the cases it may take place. Next, the ions molecules bounded by a secondary linkage means this one. I take this one as the example. So this one. Second CONH3 6 times. I take here. CONH3 6 times. What they said? The ions or molecules bounded by a secondary linkage have characteristic spatial arrangement results in coordination polyhedron. For example, cobalt is there, so it is octahedrally bonded with this nitrogen atom. So here the structure is this is octahedral structure. Okay, students. At the same time, okay, as I told you, the structure is there. That is CONH3 4 times Cl2. Before I wrote two colors are there. One is green, another one is violet. What is the reason for this green and violet color? Because if you consider cobalt here two Cl atoms are at the same side, NH3 is here, then it is one type of arrangement, it gives us a green color. Similarly, cobalt is there, again 6 atoms are there, but here two Cl atoms are at opposite direction. I hope you know cis and trans isomers. Okay, because of this type of arrangement, they give different color, green as well as violet. Okay, so in this students, this much is enough. You just remember the postulates of the Warner's theory that is important for 2 marks. Okay, once again I draw. This is just I give an example. What is primary valency and what is secondary valency for you people, and what is the spatial arrangement. Okay, so this spatial arrangement results in the structure of the atom, hybridization of the atom. So we can easily say which type of bond is there, which type of hybridization is there. Okay, this is the 4 postulates of Warner's theory, which is important, very important for 2 marks. So although Alfred Warner was the first scientist who studied about the coordination compound, hence he is called as a father of coordination compound. So in the next class, we will discuss about the different terms which we are going to use in the coordination compounds. Thank you.